Yes, for sure. Thanks for this nice introduction. So indeed, I'm going to talk about actually focus a lot on the ocean rather than on the land, and I'll explain you why. My background is indeed meteorology, so I work on weather and climate now for 37 years. The topic of data science, data simulation in Earth system models. So it's not new, it's old in fact, but we continue to do it. The plot here is a plot over the ocean in the South Atlantic. It's showing not something we directly observe, but something we can retrieve from the data that we have developed. It's spectrometer data. Spectrometers, I will talk about it. They look at the ocean surface in the microwave to the side, and the waves, the microwaves, they interfere with the ocean waves, the water. And the bigger the waves, the more signal you get back. And you can do it in different directions, and you get for the same wind speed different responses. So you also see the wind direction. So you can get wind vector data. If you get wind vector data on the ocean, you can actually start to compute derivatives like divergence and in this case curl. So this is a plot of the rotation of the wind over the ocean. And in fact, that's very important to drive the ocean motion. So there is a very strong coupling between the atmosphere and the ocean, and wind curl is driven by it. And that's why I took this plot to give you some idea of how this changes over the ocean and what we have to take account of if we want to understand the interaction between the atmosphere and the ocean. And my talk will be about that for a big part. So the title is Observing Earth System Dynamics on Weather and Climate Scales. I am, as said, Stoffelen from the Dutch Met Office, KNMI. And I lead an active remote sensing group at KNMI in, of course, the satellite department. I will take you through the history a bit of how the field has been developed and how satellites play a bigger and bigger role. So Earth observation for meteorology is really very important. So I talk about the relevance of Earth system science, about dynamical coupling of the ocean and the atmosphere, about all the satellite missions that I've worked on and that I'll be working on. I already mentioned ocean vector winds from spectrometers, but also work on different types of radar missions that can also measure wind speeds and ocean waves, sea surface temperature, ocean currents, cloud motion. I also have been involved for a long time in a unique European mission to measure wind profiles in the atmosphere with a satellite instrument. It's a Doppler wind lidar, and ESA has launched it as an explorer called Aeolus. It measures winds, clouds, and aerosol. It was launched in 2018, and it has been a big success. We're now looking for a follow-on. At KNMI, we also work on EarthCare, which is also a mission looking at 3D aspects of the atmosphere, clouds and radiation. And I'm also involved in international working groups working on cloud motion winds from geostationary satellites and from polar orbiting satellites. I've been involved in mission design, development, calibration, validation, and also comparing it to weather forecasting models. This is in fact very powerful because we can make short-range forecasts now with very good quality, and they can predict the observations that we're going to make. And of course, if the instrument fails, then it will say something else than what we've predicted. So if, as a function of instrument parameters, we look at the differences, we can actually very quickly see that something is wrong with the satellite instrument. And that's what we use very actively in the calibration of all these instruments to actually detect anomalies. Also, you must imagine that weather forecasting is an automatic process. There's no hands in there. So we go all the way from satellite observations, ground segment, processing, for example, at KNMI, to weather models. Weather models can be local models or global models. For instance, the European Center for Medium Range Weather Forecast models. They automatically ingest our released products into the model and make a forecast. And of course, if the model data, or if the observations have some kind of anomaly because the instrument failed, that could corrupt the forecast. So we have to be very safe and do good quality control to make sure that this can be done fully automatically. So I've been working on that aspect as well. Of course, we have to do geophysical processing and services because the models we employ are physical. So it has to be offered physical information. And the services do cover numerical weather prediction, but also nowcasting. So getting information to forecasters, climate services, oceanography, civil services. There's many services that profit from weather. And also user applications, particularly extremes, waves, surges, floods, storms, climate processes, climate monitoring, economy, energy, civil protection, everything is involved in there. And today we do Earth system science. So we have digital models of Earth dynamics, integrating all available knowledge and information, couple the ocean, the land, and the cryosphere processes. So the coupling is quite essential to get the climate dynamics right. When I started, we only looked at the atmosphere and we could do weather forecasts. The weather forecasts we produce today, they need good inputs on the interfaces with the land, the cryosphere, and the ocean. So the coupling is complex due to processes on different time and space scales. So the weather is very fast, the ocean is a slow fluid, and the land is, you could say, even slower. The ocean is very important because it's more than 70% of the Earth's surface. So if you want to think about climate change, you first have to consider the ocean. This is maybe a bit counterintuitive because we sit on the land and we think we see things change, so we should investigate it. But everything happens in the ocean, you could say. So if you think about climate processes. We need measurements for initialization and for learning all detailed Earth processes. We have more and more satellite data to integrate into these models. I mentioned the ocean and the atmosphere that determine to a large extent Earth system dynamics. The ocean stores carbon, it stores excess heat, it has the water, of course. So all the important things that determine climate change are actually in the ocean, absorbed by the ocean, provided by the ocean. So the ocean is really key. So 85% of atmospheric water is actually evaporated from the ocean, and 75% of the water falls back in the ocean. Earth system dynamics can be quite disastrous. This is a study based on physics-based early warning signal showing about the Atlantic meridional overturning circulation. It recently has been in the news again in the Netherlands. And the reason why we put it in the news is it's on a tipping course. So there has been model studies that have improved, let's say, physical aspects that show the slowing down process of the Atlantic meridional circulation. And key indicators show that the real world moves toward the modeled AMOC collapse. So we have, of course, models that can predict, but we also have observations. We want to compare them, and if we see that they are close and follow each other, then we have more confidence, of course, in the prediction. A collapse would happen relatively fast. That means 2060, and would be really disaster for Western Europe. So let me hide this one. So the question is how to deal with unknown risk, because it's very difficult to put a good number on the risk. So we know the risk is real, but the impact is very high. So if this happens, the changes will be faster for Western Europe than climate change changes. So it is induced by climate change, but if this change happens, things in Europe will change very fast, which is of course a big risk because everything will change. We are used to our current climate. If our current climate changes, then we are in panic. Yes, that's heard a lot of times. That may be a happy news for some people, but I think it's bad news for most other people. So the consequences are on the next slide, for example. So here you see, let's take the green line in Bergen. On the right plot, it's the temperature change in a century. And February, it says -35. I'm not sure if you can appreciate the number, -35 colder. It is, it's like moving from Netherlands to all the way to the North Pole, yes? Or bring the North Pole weather to the Netherlands, something like that. That's the change. It's really huge. Of course, Bergen is hit hardest, and you could look at Madrid in Spain, and there the model predicts something that is like compensating for global warming in Spain. Yes, because let's be clear. Yes, this is caused by carbon increase. Carbon increase, if it continues, will continue global warming. Yes. So global warming will continue. So we get sea level rise, we get rising global temperatures, but in addition, we get a cooling of the North Atlantic because the Gulf Stream will slow down and stop. Currently, the temperatures in London on a yearly basis are about 15 degrees higher than the same latitude in Canada. That is due to the Gulf Stream. If you take the Gulf Stream away, the temperatures will drop dramatically. So the main reason this could happen is that we get more runoff and melting of glaciers in Greenland. So we get fresh water into the ocean that changes the convection in the ocean. The convection in the ocean is a trigger for the circulation. Of course, you have continuity. So where water comes down, water has to stream in, and that's warm water from the south. The change will also make that less heat from the southern hemisphere will be transported to the northern hemisphere. So the southern hemisphere will stay warmer. That is not so good for the ice on the southern hemisphere, which is enormous. It is 40-meter sea level rise if you melt all the ice or even more. So it's not good news for the Netherlands, because if you melt water on the South Pole, due to gravity, this water actually flows to the northern hemisphere. It doesn't stay in the southern hemisphere. It flows to the northern hemisphere. So dramatic, as I say. Yeah. So how do we know this? How can we understand this? Can we do research to better comprehend what's going to happen, and can we take measures? Of course, we do a lot of climate research, and we know a lot of climate change. But if you and the things that we are in an energy transition, so it helps to motivate people to change things in the world. I should say not everybody, but you can see that many things are happening due to the knowledge of climate change. So getting the knowledge is important. So what about all these dynamics? We have the atmospheric dynamics that has been, let's say, for our institute, of course, the classical thing to look at to understand weather and climate. So in climate change, we talk about carbon. This gives temperature changes, radiation changes, it changes atmospheric stability. So it tends to warm the upper air. The upper air is very cold. If you warm the upper air, the atmosphere gets more stable. So it has effect on actually unstable weather. But also it has effect on humidity. If you increase the temperature at the surface, you get more moisture in the atmosphere. It's a nonlinear process, let's say. So a little bit of increase in temperature gives you much more humidity. Humidity at the surface increases instability. So that is sort of compensating the effect of the stabilization due to the temperature profile. So higher humidity means that we get clouds and more rain. So more rain is really a problem of climate change. So IPCC says that if it's dry, it gets drier because of more evaporation. If it's wet, it gets wetter because there will be more rain. There's more water in the atmosphere. Yes, so nothing changes, but only humidity. This is what you get. Of course, the question is, do dynamics also change? Because every place on the Earth is adapted to the local climate. So if the local climate changes, then people have to adapt. Infrastructure has to adapt. Nature will adapt. Everything adapts to a changing climate. So it's not only about the global mean, it's certainly also about local circulation changes, because they actually have most of the impact on people's lives, not the global change. Yes? So I gave the example of the AMOC. It's clear that if the AMOC happens in the North Atlantic, it has dramatic consequences for people in Western Europe, but not so much for people elsewhere. Yes. So local circulation changes are really very important. We have hurricanes and tornadoes. Will they change path or intensity? We have jet streams and climate zones. Jet streams cause winter storms. Do winter storms change? This is all, of course, very important to know. We have ocean carbon exchange. So currently the ocean is absorbing a lot of carbon. Will that stay the same if we change the climate? Or will richer carbon from the ocean get to the surface and it will not absorb it anymore? So these questions are very important. Ocean heating. So the heat we produce now in the atmosphere by carbon is actually put into the ocean to a great extent. But we also have evaporation and cooling. So what is the balance and how can it perhaps change if we have climate change? Yes, these are very important questions. I show a process here below, which is moist convection. Moist convection is a process where moist, warm air near the surface actually goes up. Because the upper air is cold, so warm air is light, cold air is heavy. So if you create warm, moist air near the surface, it tends to go up. If it goes up, it condensates, so you get clouds. If then this releases or this heats the air, in fact, so it will go up even faster. So this is an active feedback on air going up. So that will, if there's more moisture in it, it will go up faster and longer. So you get a deeper convection. This is very important process, of course, because it changes tropopause height. It can change the distribution of water vapor in the atmosphere. Water vapor is a stronger greenhouse gas than carbon. So if you change the distribution of water vapor in the atmosphere, it changes the climate problem. And moist convection is a key process to bring up water vapor from the surface all the way up in the atmosphere. So understanding moist convection is really important. And I will go a bit further into it. Consequences of climate change we see on the news, I would say almost every day. The local climate getting out of balance with the previous climate, getting consequences people did not anticipate before. This is something that is, so the question is, how much worse can it get? That's really the question. If you get bad weather, of course, it's very good to make better weather forecasts. We do. So we can improve weather forecasts. And here you see a timeline from 80s to 2015 almost. The curves just continue. So the message since the turn of the century is that we put in satellite data, and inputting in satellite data helps us to sustain improving weather forecasts. You see two curves here, but first you see colors. Let's start with the colors. So blue is day 3 forecast, red day 5, green day 7, and orange day 10. And on the vertical axis, there's a measure of accuracy of the weather forecast. So you actually test the weather forecast against the weather analysis and see how good the forecast is. And you see that the accuracy actually is increasing by about 1 day in 10 years. So, and that is something we can sustain. So now you see at the bottom of the plot also day 10 coming up. even day 10, we get some accuracy that is useful. Today, I mentioned the turn of the century as satellites. So you see there is a kink, and that is caused by satellite data. So we get more observations, we can better use them, but also we get bigger computers, of course, and bigger computers imply better weather models, and that helps us a lot. Satellite instruments are very important. So here you see all kinds of instruments, and majority of the instruments we use today, about 100 different satellite instruments are used in near real time for weather forecasting. So it's a very complex operation, ingesting all these different types of data. So the remaining question is, of course, what observations are particularly needed to make further improvements? What do satellites observe? They observe both near real time and offline. So we also can use some satellites for climate analysis. They have large spatial coverage. We have polar satellites. Polar satellites are often sun-synchronous, not always, but often. In that case, the Earth turns below them. And that means you get ascending and descending orbits. So 2 times a day you get coverage from each satellite. If you have many of them, of course, you can cover all times of day. And this is how we can track the weather. We have furthermore above the equator, we have geostationary images. So in daylight, we have visible images. They are the oldest weather images showing cloud movements from geostationary position. The geosatellites, they have the same rotation as the Earth. So in essence, they stay fixed on a position above the equator. And therefore, we can do a high temporal revisit for the locations seen from each satellite position in geostationary position. Now we have constellations between geostationary and polar orbiting satellites to cover all the aspects of the weather, both the temporal, spatial aspects. We get winds, waves, storm surges, sea surface temperature, ocean color, water quality, cloud aerosol, rain, lightning, and bathymetry. So we have a lot of measurements we can put into our models to improve the processes, but also, of course, important to initialize the weather condition as it is now, because all the weather forecast improvements arrive from better initial conditions, so from observations. We need observations to do weather forecasts. We now move to machine learning techniques. There's the same thing. We need observations also for machine learning techniques to make forecasts of the weather. And I would even argue we need much of the same observing techniques, because the observing techniques that we require are based on physical principles, and the physical principles will stay there. You can do machine learning, but you cannot beat the physics. So physics are rules that we established well to great accuracy, and machine learning has to learn them, because otherwise it will fail. So what observations contribute? So when I started working in 37 years ago, I started to work on wind, and I discovered very quickly that wind is actually very important because of the dispersion relationships of the fluid called atmosphere. You can argue that if you want to go to smaller scales, you need to look at the derivative of the mass field, which is the wind. Because then if you get wind information, it's more powerful to initialize the dynamics of the atmosphere. And guess what? Today we have wind observations that per observation contribute the most to weather forecasts. So I already mentioned Aeolus, which I worked on. It's a space-based wind lidar. It makes wind profiles in the atmosphere. Per observation in red, this is has the most impact. Then we have the spectrometer winds, I also mentioned. We're working on them at KNMI to get winds above the ocean. Per observation, most powerful to initialize weather forecasts and make accurate forecasts. Then we have radiosondes, also measuring wind. We have a ground-based radar, which is precipitation. Atmospheric motion wind vectors, I also talk about them. Again, wind and aircraft wind. So then we get all the microwave on water vapor, temperature, etc. that per observation have less contribution, but we can make many of them because they are easier to make, these observations. So in total, if you look at the blue is what each system is contributing in total, which depends, of course, also on the number of observations that we put in. And at the moment, we put in a lot of infrared and microwave observations for initialization, and you can see therefore all the large blue bars. We make these analysis, diagnostic of what is important to improve weather forecasts. This is fed back to the World Meteorological Organization. They have tables with capabilities for each application, for each variable, and they have tables with requirements. Of course, then you can compare them. You can compare capabilities and requirements, and you can look for a statement of compliance. And of course, if there's no compliance, or you can see in which areas we can improve things because we need more capability with respect to requirements, you can put that in a vision. And this is the 2040 vision at the moment from the WMO, saying what we need to improve weather forecasts. And of course, I'm also involved in this process. This is just a movie. But it's interesting. It's low clouds and high clouds. High clouds with rain in yellow. And it's not playing automatically, but I can trigger it again. So what you see here is a lot of movement, of course. And you can try to follow. Oops. You can try to follow a cloud particle and see what happens to it. And I encourage you to do that. And another aspect which is very clear is that if you look at motions, you see motions through each other, it seems. So things seem to move in different ways in one location. And this is what we have to forecast, of course, because you want to know where the clouds are. So we have to forecast this. Well, we can use machine learning, yes. So who thinks that if we use optical flow on this image, that we can make a good wind forecast? High quality. Just based on the image? No physics? Can you think you do optical flow and we do a very good wind forecast? Can you imagine that? Yeah, can we, on the basis of this moving picture, can we beat the physical model, do you think? Any idea? Yes, you could say, I don't know, or maybe raise your hand if you say, I don't know. Raise your hand if you think, oh yes, this must be possible. Okay. Good. Yes. I can explain why it's not possible based on physical principles. Because if you follow cloud particles here, you see they appear and disappear. Yes? They don't stay there because air moves up and air moves down. If air moves up, you create a cloud. If air moves down, you dissipate the cloud. So how do you deal with sources and sinks in your machine learning code? You no idea where on the basis of the image, you don't know where the cloud is going to appear. Maybe you have some skill if you look at the pictures carefully where it's going to disappear. But there's no way you're going to find out where it's going to disappear. You have no way how to find where it's going to disappear, to appear. So, and then you have clouds at different levels. That's why the motions go through each other, because the wind is different on different levels. Actually, the wind changes a lot from the surface to 10 kilometers height where the clouds are. And if you look at the image, all the motions go through each other together with the optical properties. So how is the machine learning going to disentangle the optical properties from the wind motion? There is no way physically. It's aliased. Yes? You cannot undo aliasing if you don't have information about the reason why. Yes, so then you need the physics. So based on the physics, you can understand that there are winds at different levels, and you could try to figure out whether there's some way to do it, but then you find out it's not possible only on the basis of the image, because we cannot do accurate height assignment based on this image. We can do it only in a very approximate way. So that means that we cannot beat weather forecast, because if you cannot do height assignment within an accuracy of a kilometer, then the wind changes 4 meters per second per kilometer. So we cannot do a better wind than 4 meters per second, which is not good enough to make a weather forecast. So this is why I can argue that you cannot do it based on the information content that is in the image. But it's reasoning from information content and physics. So that is important to do that. Yes. So we do get winds from images, and we use them, but it needs a lot of quality control, a lot of constraining, and then we can use 5% of the winds we compute, so the rest we throw away. And we use machine learning techniques to get the winds. We can get winds at different heights, and they're no way as good as the weather forecast model, but because we get many of them with reasonable random errors, we can sort of still exploit it to some extent in weather forecasting. And they're really abundant. They're everywhere, because we have a lot of images and infrared sensors that can do these winds, but we can only exploit a few of them. So then we have the Aeolus Doppler wind lidar. It's a laser. It is range gating. So we get, as a function of height, we get different. We get a laser return. The laser return is actually Doppler shifted because of the air moving. So we can get the movement of the air from it. So here you see what we call Rayleigh wind. Rayleigh wind is very unique because it determines the motion of molecules. And that is in clear air. In clear air, there's very little you can do to measure the properties of the air. But the Doppler wind lidar can actually measure the Doppler of the clear air. And we've done that, and you see an image here. And if you look at the image, it goes up to 20 kilometers height on the left-hand side. You actually see that most of the air is clear. Yes? Most of the pixels are filled. It's a laser beam at 355 nanometers, very short wavelength, because it has to see the molecules. And at 355, of course, any cloud will block the signal. If there's optically thick clouds, then we will not see below. But you see that we get many winds. On the right-hand side, we also measure the particle winds. So particle winds are winds that are based on clouds, mainly. Also some aerosol, low in the atmosphere. So you see there's almost no clouds in the atmosphere. Yes? You may then question why. Well, the reason that this is the case is that most of the clouds are actually close to the surface, yes? And if you look from the bottom, you see all these clouds close to the surface, so it looks always very cloudy, particularly here in the Netherlands. But if you look from the top, then most of it is actually quite clear. So we get a lot of Rayleigh winds, and the Aeolus atmospheric return was much lower than we expected from the design. But still, we were able to prove the impact of these winds in the numeric weather prediction. I already showed a plot of it, showing that per observation they are very important, but also as an instrument as a whole, we got about 5% of the contribution to the forecast impact. And since we use 100 instruments, getting 5% from one instrument is very high. And the global community was very pleased with it. So this is about the wind errors. They were like 5-6 meters per second, which is very high wind errors, but the errors are random. So we could still exploit it, as I showed, and the instrument was very important. But we can also build an instrument, we are now more confident, that can have measures in the order of 2 to 3 meters per second. So then the question is, how much will the impact increase? And we do some projections. And here you see a few projections going to the left with smaller wind errors and getting more impact. So this goes back to the issue of clouds. So how does Aeolus complement these feature tracked winds? And on the right, so we have techniques that can range and they can give you the exact height of the clouds. And we have techniques that work only with images. So they have to get the cloud height from the radiation properties. And you can see that, for example, on the top, these are two visible instruments. One is MISR, it's doing parallax determination of height, and the other one is GOES, which is a visible imager from the US. And if you plot the heights to the two instruments of collocated points, you get a scatter plot over there, and you see there's a lot of spread. And the spread is not very good because the winds change with 4 meters per second per height on average. But of course, in cases with jets, the wind change over a kilometer can be much higher, like more than 10 meters per second or 20 meters per second. And then if you make an error assessment of 1 kilometer, of course, the wind error is very big. And in particular, these jets are very important. So it's actually very important to get the wind shear right to understand the dynamics of the atmosphere, because wind shear is causing mixing in the atmosphere. So that's the thing we want to know. We don't want to know the wind in the upper air. We want to know the shear. So if the height assignment is not good, the shear is very bad. Height assignment is good, we get better shear. And that's why Aeolus was so important, because it provided this information. Then I talked about parallax. So you can have views of a cloud from 2 different directions. It will project the cloud on a different position on the Earth. So if you know the positions of the satellite and you know how the cloud is displayed on the Earth projection, on the surface projection, then you can compute the height of the cloud in principle. The problem is if you use 2 satellites and there's time in between, then you get aliasing between cloud height and cloud change. Yes, the cloud can change in height, or it can move, or can grow. So you need the measurements at the same time. So now in Europe, we are going to do a mission where we have an infrared instrument on 2 satellites, A and B, measuring at the same time, and with having many views. So now we are going to look at cloud boundary motion on, let's say, typical 100-meter scales. So we try to understand cloud dynamics in relation to the wind. And that will help us to better exploit all these images, of course, but also to get a good height assigned winds from satellites. This is in the Harmony ESA Earth Explorer 10 mission that will feature these tandem satellites with multi-look infrared instruments. This is an example of a hurricane. You see this is a hurricane shield. You look at the top and you see some popcorn. This is convection that's coming from the bottom and hitting the cloud shield and then making some structure. And of course, if the air comes up and hits the cloud shield, then there will be flow of air left and right. And that's what we measure with the tandem satellite and the stereo winds. This is only one component that is measured because this is one satellite, and the other component is difficult because of the cloud transformation that I mentioned before. But you clearly see the wave that is generated by the convection in the tropical cyclone. And of course, that is important for the tropical cyclone dynamics. Then EarthCare. So EarthCare has been launched last year, and we get first data. It also has a LiDAR looking down, looking at aerosol and cloud. But it also has a radar looking down. So the radar can look into the clouds. So that's how you get the plot on the top right. In the top right, you see actually convection. So you see this is the result of air from the surface going up, rising, spreading, and you see the rain also. The rain is, let's say, hitting the surface, of course. So you see it going down. So the radar is well capable of measuring this. You see the melting layer, which is the line you see in the plot. So you see many things, many aspects of moist convection that are difficult to physically model very accurately because of the huge variability in moist convection because of the turbulence that is associated with it. There's a relation between turbulence and thermodynamics in the clouds, and that is difficult to physically capture. And these instruments will tell us in a better way how coagulation, how ice and water mixing, how this is going, and to improve the physics of the clouds. Physics of the clouds is very important for climate dynamics, because if clouds resolve when the climate warms, we get more sunshine on the Earth, more heating, so it's immensely important. But it's also regulated by the dynamics. So how the wind goes and the turbulence goes through these clouds is very important. And I will go to that in the next slide. So on the right-hand side here, you see a scatometer plot, actually two. And here you see convection. So the contours are rain retrieved from a geostationary satellite. And we have that every 15 minutes. So now we can start to relate the snapshot of the winds, which are the red arrows and the blue arrows. These are actually two satellite acquisitions of the wind field at the surface, separated by 50 minutes. So only 50 minutes. And you see that when there is rain, the winds change substantially in 50 minutes. And when there's no rain, the winds stay more or less the same. So this is the process of moist convection that causes this change. Moist convection has updrafts, so winds from the surface, at the surface, that converge. The winds at the surface that converge, that are over the ocean, are always moist, because wind helps evaporation. So, and also it takes the heat of the ocean. So these are moist, warm winds. And if they go up, we get convection. So if the air is warm enough to go up, then it will cause condensation and rain, and it will cause further towering of the convection to greater heights. So the more moist and the more heat, the higher the cloud goes, depending on the total stability, of course, also. But then rain forms, and rain is heavy and falls down. So you get rain and ice that's coming down. It's the temperature at the top of the cloud can be minus 80 degrees in the tropics. So it's very, very cold. And if that falls down, it of course cools the air at lower layers, which can be 30 or 20 degrees above zero. So this cooling also implies drying, because although the downdraft originates from wet precipitation, it's at very cold temperatures. So the dew points are very low. And if then the air falls down, it maintains the dew point and it comes down to the surface. It's very dry air. So it's cold and dry air that's coming from very wet clouds. But it sounds contradictory, but this is how the process works. So what the process is doing is bringing warm and moist up into the air, but also bringing cold and dry down to the surface, and really over very big areas. These are called cold pools. And cold pools are very big areas over the ocean, where cold and dry air is brought down by moist convection. And it's with gusts spreading over the water over hundreds of kilometers. And of course, this air will evaporate, and the wind will evaporate water from the ocean, because it can contain a lot more of moisture. And so it cools the ocean because of the evaporation. There's the water from the moist convection is refreshing the ocean. So the salt water gets sweet, because the sweet water is coming from the rain. And we see this process of moist convection in scatometers, as you can see on the right-hand side. And on the left plots, we show this. So we looked at extreme rain and extreme convergence and divergence, and then see how it's associated with rain in time. And we see actually that the divergence, so the updrafts, they appear before the rain, as you expect. And the downdraft, the downdraft, so the winds coming down, they appear after the rain, as you also expect. And that's what you see in the plot on the left. So now we have a vehicle to look at this more systematically and better understand the processes. And then in combination with this Earth Care mission, it can also look vertically down. We can get an idea of the vertical fluxes in the clouds when there is a cloud, because the mission does not see the downdrafts because there's no cloud. But the downdrafts we can estimate from scatometers. So now there's We have more and more data to better understand moist convection and the replacement of moist, the very fast replacement of moist warm air with cold and dry air in the tropical ocean. We get now more information about. Yes, we also see this in hurricanes. So also in 15 minutes, you see how the convection in the hurricane changes. That's very important to understand the dynamics and the evolution of the hurricane. We do the spectrometer processing at KNMI in a worldwide wind service. So we produce level 2 wind products, as I showed in this plot and the previous one, with an international constellation of satellites. Currently, we have Chinese, Indian, and European satellites. We process all of them at KNMI, and they go all over the world to be used for weather forecasting. So we directly contribute to improvements in weather forecasts. Timeliness has to be very fast because it's for initialization. So 30 minutes to 2 hours. We even have now 15 minutes winds. And we use, so we produce level 2 software for EUMETSAT, and then we have level 3 and level 4 data in the Copernicus Marine Service. And these are also available, of course, in the Copernicus services. And you can get more information on this. Also, the software is available, so we make our processes open. So as I said, it's very important for hurricanes. And since we have now 7 spectrometers that we process, sometimes we are lucky with the landfall of a hurricane, and we can look at the consistency of the different spectrometers. And from that, we learn how to improve the winds and the services. Also, there are some sensors that have higher resolution, but lower quality of the winds. But we can learn the spatial structure functions of tropical cyclones from it. And then we can do resolution enhancement. Here you see an example. So the top plot is a spectrometer plot, which is resolution enhanced. And the bottom plot is the SAR wind field that we used. We used many SAR acquisitions, 150 to learn from. And the time difference between the 2 plots is 3.5 hours. So you see also how the structure has rotated a little bit and extended into 3.5 hours. So we don't learn the cyclone complete, but we learn the structure of the cyclone, and that helps us to enhance the resolution. We can then make triple collocation. That's also something we do very frequently. So if you compare 2 things, you never know where the error is. Is it the system X or Y? If we do triple collocation, we have 3 things to compare, so we can actually assign errors to X, Y, and Z. And that's what we do here. So for example, on the right-hand side, you see comparison between the synthetic aperture radar at high resolution, spectrometer at moderate resolution, and the ECM forecasting model. And after doing the calibrations, which you can see on the left and in the middle, you see that the error for very high winds is about 10% in ASCAT and about 15% of the wind speed in SAR and ECMF. So we, of course, try to comprehend these results and statistical results with what we know about the measuring systems. And that's one thing we do. We also extend our systems to go closer to the coast. Coastal winds are, of course, also very important for infrastructure. And we manage to do that. And then we also do the triple collocation data on the global winds to look at the accuracy of the spectrometer winds, which proved to be very accurate, particularly European spectrometer. Then if we have these accurate winds, we can compare them to models, and we can do that globally. And if you look at these plots, you see red and blue areas, which are model biases. This is for error 5, which is the main reanalysis of the European Center for Medium-Range Weather Forecasts at the moment. We also now working with them on the next one, error 6, and even on error 7, trying to exploit the spectrometer data to improve the reanalysis. And here you see how the biases in the zonal wind at the top and the north-south wind, the meridional wind at the bottom, how these evolved over time in 2022. So the first column is for January, then April and July and October. And particularly in the meridional wind, you see that the bias patterns are very persistent over all seasons, but also there are some changes. The differences you can see on the right-hand side, they are more than 1 meter per second over a whole month, which is a lot. because the accuracy of spectrometer is like 0.5. So the model is really has very large biases. Very large biases in the surface wind imply that you push the water in the ocean in the wrong direction, which of course implies that the coupling between the ocean and the atmosphere is not correct. So you will simulate the wrong currents. And of course that will also distort the dynamics. So we also are trying to understand how this is distorted and how we can improve this. And also here we can use machine learning techniques to do sensitivity experiments. It's not only the mean that has biases, as you can see here in another plot at the top in the wind speed, but also the wind variability is missing in global models, as we can see it from spectrometers. So that's in the lower plot. So there's an annual mean meridional wind speed difference and the transient speed difference between spectrometer and error 5. And also the transient differences are quite large, particularly in areas that are meteorologically active. And that's where all the exchanges happen. So that's where the fluxes are and where the dynamics play a big role. Then there's a coupling between the ocean and the atmosphere, which is the currents. So the winds, you will experience the winds if you are on the ocean relative to the currents. So you will not feel the real, let's say, wind with respect to the Earth reference because you don't have an Earth reference. It's the same for a spectrometer. It measures the roughness of the ocean, which is related to the relative wind between the ocean and the atmosphere. So if there's a current, then the current will be implied in the winds. But the model actually computes the wind with respect to a fixed Earth reference. So if you have the currents, if you can measure them, you can add them to the spectrometer winds, and then you would expect that the errors reduce. This is what has been done here. At the top for the speed, one is before correction on the left and after correction at the bottom. So the colors are again the wind differences, and the black contour lines is the current. And what you see if you do the correction is that the pattern is moving, but the amplitude of the errors stay the same, more or less. But now the pattern of the error is more consistent with the contours of the current. So it seems to be physically more plausible and better to explain maybe in parameterizations. Then at the bottom, you see the same for the curl. So for the wind curl, which is rotation of the wind. And now it's even clearer that the errors in rotation are associated with current gradients. Now after this correction, we have, so the large-scale ocean currents do make sense. We get from altimeters, not the small scales, but the large scales, more than 150 kilometers. And if we use them, we can get observations and models closer together, but the biases in the models are staying. They're not getting smaller. So now we have this new mission, Harmony, which also looks at the ocean surface. We use this plot for the balance between the ocean and the atmosphere. So balance in heat, gas, and momentum. There's all kinds of organization at the air-sea interface. Organization in both the ocean and in the atmosphere will cause more efficient exchanges between them. So if we don't capture this well, then we may make actually large mistakes over the globe. So these are small scales, but they are the mechanisms of the processes which we need to capture also on the global scale to understand the coupling between the atmosphere and the ocean. And now we get more and more observations to look at this in small scales. As I said, it's more than 70% of the Earth's surface, and the coupling is very important to understand the dynamics of the climates. And the real question is, will the modes that we know, will they change in a changing climate, and with what consequences? There's also a nice journal paper article rising from the Antarctic, Climate Alarm, about winds and about how the wind forces the ocean, how the ocean forces the ice, effects on heat and carbon and ice and land ice and sea ice. It's a very nice, I think, contribution, easy to follow, with a lot of, let's say, illustrations. So I can recommend it. I provided a link, so if you have the file, you can look at it. And this is where I want to conclude about Earth dynamics from space. So winds determine hurricanes, weather, wave surges, wind power, ocean forcing, heat, carbon budget, sea ice decline, climate change. Wind and wind shear and wind derivatives are very important for these exchange processes. And they're also used by marine forecasters, numeric weather prediction, oceanographers, wind engineers, offshore industry, safety authorities, climate scientists interested in dynamics. We get more and more through international exchange. Also, China is now planning on a Doppler wind lidar system in space based on the positive experiences from Europe. It's a very technical development, but going very, very fast, at least in my career. Data science has been very prominent. So all the things I've shown has been done with data science because the physics is not good enough to do it. So I've been working with data science in all my career, and recently also with machine learning. We use it for both monitoring quality control applications. We can well use new satellites, but certainly more resources for improved exploitation of existing satellites in society. And open services and computer clouds allow Earth collaboration and further scientific programs. So the motto is share the Earth, its satellite, its science, and its services. You can read more about the KNMI work and my work in these references, which I put here. And here I want to end my presentation. Thank you.